Yes. Good. Okay. Good morning, everyone. Now we are recording. So, unfortunately, due to the regulations, today's lecture is at 8 a.m. And it just so happens that we are probably doing one of the most intricate and elegant proofs in this course at during an 8 a.m. lecture. So, apologies for that, but that's just a coincidence. Okay. So, what does Thomason's theorem say? It says that every three connected graph has a contractible edge, so long as it has at least 5 vertices. Okay? And what is a contractible edge? It's an edge in a three connected graph, so that when you contract it, you preserve the three connected property. Okay? So let's introduce two more definitions. An edge of a three connected graph is deletable if after deleting that edge, the graph is still three connected. Okay? Now you see, when you delete an edge from a simple graph, the resulting graph will always be simple. Okay? So if we find a deletable edge in a simple three connected graph, we are done. Tutte theorem has been proved. But that's not true for contraction. If your graph is simple, contracting an edge may create multiple edges. So because of that, I'm going to introduce a new definition. For a simple three connected graph, we will say that an edge is strictly contractible if after contracting it, you maintain both the properties, simple and three connected. Okay? So with these definitions, Tutte's theorem is saying that in any simple three connected graph that is not a wheel, you can find an edge that is either deletable or strictly contractible. Okay? I decided to introduce a new definition after posting the questions on Piazza yesterday. So this is not consistent with the definitions I wrote on Piazza last night, but I will change it after the lecture. Okay? Is everybody happy with the definitions and the statement of Tutte's theorem? Someone raised a hand, maybe. Ananya, yes.
Yes, sir. So I have a question. So your question is for, so we did a characterization for using Thomason theorem. A graph is three connected if and only if there exists a sequence G0, G1, G2, Gr.
Yeah.
So an analogous thing can we just say for simple three connected graphs?
Yeah, that is what, yeah, we wrote that yesterday, right? We wrote a generation theorem for simple three connected graphs. Graph is simple and three connected if and only if there is a sequence, blah, 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 right?
Okay. So the starting point, the starting graph of the sequence must be a wheel.
Yes, it will have to be some wheel. Which wheel, we don't know.
Which wheel, we don't know.
Yeah. Depending on the graph, you could have to start from a very big wheel. If you insist on starting from a smaller wheel, you will have to allow parallel edges, which is why we cannot do that.
Okay. And at every stage, Gi plus 1 either has an edge that is deletable or strictly contractible.
That's right. Yes.
And all elements in this sequence are simple drops.
Yes, all of them will be simple and three connected.
Okay, simple and three connected. Okay.
Okay. Good. Any other questions or concerns? Okay. So please keep all the definitions in mind. I'm using these definitions so that I don't have to say long statements again and again. Okay. Good. So now our next goal is to prove Tutte's theorem. Tutte's theorem. Okay. So how do we prove a statement like this? How do you show? So let us suppose, let G be a three connected graph, simple three connected graph. Sorry, I keep forgetting this important detail. It's a simple three connected graph that has no deletable edges and it has no strictly contractible edges. Okay, our goal is to show that G is a wheel. Okay. So already you can see that this is a result, this is the kind of result we have not proved in this course so far. We are trying to show that there is a very specific family of graphs, the wheels, right? This is not the complete graphs of the cycles that are much more basic in a sense that you see in the beginning of a graph theory course, right? The wheels are a very specific structured three connected graphs. And we are showing that these are the only three connected graphs, simple three connected graphs that do not have deletable or strictly contractible edges. So somehow we need to construct the graph G, we need to argue about the structure of G, and we need to show that the only way this is possible is if the graph is a wheel, right? So it's quite different from anything we have proved in this course so far. But at the same time, it is a canonical result in structural graph theory. We have lots of results in structural graph theory that look like this. Okay. All right, so what we are going to do is, we are going to prove this in a few steps. I'll call them, I'll give the steps names. Our first step is to show that a certain structure exists in this graph. Okay, G has a certain special substructure. You can think of substructure as a subgraph with special properties. Okay. Again, the statement of the step will become more clear as we complete the step. Okay. Okay, so we have a three connected simple graph. We can assume that the graph has at least 5 vertices, because otherwise it has exactly 4 vertices, because it's a simple three connected graph, and then it will have to be K4. Otherwise, G is equal to K4, and there is nothing to prove because K4 is a wheel. Okay, that is the only simple three connected graph on less than 5 vertices. You can check that. So if it has at least 5 vertices, then by Thomason's theorem, it has a contractible edge, right? By Thomason's theorem, G has a contractible edge. I'm going to call this edge E0. Okay, you will see why I'm calling it E0 in some time. And let's call its ends V0, V1. Okay? So this is the edge E0, V0, and V1. If this edge is strictly contractible, which means when you contract it, you get a simple graph, then you are done. Then you have proved Tutte's theorem, right? So we may assume that this edge is not strictly contractible. We may assume that E is not strictly contractible. Otherwise, we are done. There is nothing to prove. In fact, no, otherwise actually we get a contradiction because we assume that all the edges are not strictly contractible. So the way I am writing it, it's not a contradiction. It actually follows by our hypothesis. Sorry. Okay. Is everybody with me? What does it mean for the edge to not be strictly contractible? Can somebody tell me what does this imply?
That means the endpoints
multiple.
of
Yeah.
common neighbor.
Okay, so in the contraction, it means that we get a parallel edge like this. Notice that the only way you can create a parallel edge in the contraction is at the contraction vertex. Okay, so if this is my contraction vertex Z,
So basically, there will be a triangle in the original graph G having the
Exactly. So if you go back to the original graph, what will it look like? It will look like this, right? If this is the vertex W, then W will be a common neighbor of V0 and V1. That is the only way you can get a parallel edge in the contraction. Okay? This was one of the do-it-yourself exercises from last night. This implies that V0 and V1 have at least one common neighbor. I'm going to call this common neighbor H. Okay? Let me change the W, it's H. Sorry. Okay? And we can say this for every contractible edge, right? So we will repeatedly apply this argument to other contractible edges when necessary. Okay? Typically, I would make a small lemma out of this, but I don't have the time for that. So I'm omitting those kinds of aesthetic details. Okay, good. So now what we are going to do is we are going to try to argue about the vicinity of this edge E0. Around the vicinity of this edge, we are going to try to study this graph and to get some more conclusions, okay? That is we are trying to establish a certain substructure. So this will be around the edge E0, okay? All right. Let me look at this edge, HB1. Let me call this F. Okay. Consider F to be the edge HV1. Okay. If we delete this edge from the original graph, we will get a simple graph. That is true for every edge, right? Because the graph is simple. You delete any edge, then the graph will still be simple. Which means, if we delete an edge, the graph cannot be three connected. Okay? That is because of our assumption that the graph does not have any deletable edges. Okay? Note that G delete F is not three connected. This is actually true for every edge of the graph by the fact that there are no deletable edges. G delete F is not three connected for all edges of the graph. So whenever you delete an edge, you will create a two vertex cut. Okay, because the graph will not be complete because you have removed an edge. So if it is not complete and it is not three connected, then it is because it has a two vertex cut. Okay. So let us try to understand. The point is we have some information about the structure of this graph. So we are going to use this in the context of there being a two vertex cut after deleting the edge F. Okay. So what happens? In the graph G minus F, there is a set of two vertices that will disconnect the graph into some number of components. Okay. I will convince you that there has to be exactly two components, but there are at least two components. Now this vertex cut S cannot be a two vertex cut in the graph G. What does that mean? Can anybody tell me what this means? S is not a two vertex cut in the original graph.
Sir, I have a question.
Yeah.
If it was, it would not be three connected.
Right, but what does it imply? I want to say something about the edge F.
Sir, I
It
have a
is
question.
non-contractible.
Okay. Yeah, Ananya, what's your question?
So why G minus S will have exactly two components?
I am not saying that. I said there could be many components. I am drawing just two components. There could be 5 components, right?
Okay. Okay,
Okay.
sir.
But my point now is, where is the edge F? Can somebody tell me where is this edge F?
The edge F must be in either, means the endpoints of the F, both the endpoints of F must be either in the same component.
No, that can't be. If both edges of F are here, this would be a two vertex cut in the original graph.
So I think one endpoint would be in the set S and the other endpoint would be in some component.
No, if it is like this is still a two vertex cut.
Both the endpoints must be in the set S.
No, then it is still a two vertex cut. So what's the only possibility remaining? You have tried all the possibilities. What is the only possibility remaining?
One endpoint in one component and the other endpoint.
Exactly. It has to be like this. That's the only way you can destroy this two vertex cut in the original graph. Right? The original graph is three connected, so you cannot have two vertex cuts. So the edge F has to have its two ends in two distinct components of G minus F minus S. And that implies that there are exactly two components. F has its ends in distinct components of G minus F minus S, and this in particular implies that G minus F minus S has precisely two components. Is everybody with me? When we delete the edge F, we get a two vertex cut. The only way this two vertex cut would not be a two vertex cut in the original graph is if the edge F that we removed has its ends in two distinct components of G minus F minus S. Okay? And that means that there are exactly two components because the edge F has only two ends like every edge in a simple graph. Okay. If no other questions, then let's put down the labels. So let's say this is the vertex V1 and this is the vertex H. Remember F is equal to HV1. Well, but they have a common neighbor, V0. Where is that common neighbor? Where can the common neighbor be? H and V1 have a common neighbor. Where can it be? So now this is not G minus F. This is the graph G now because we added
It has
the
to
edge.
be in S.
It has to be in S. Exactly. The common neighbor has to be here. V0. Right? Great. All right. So we have this much information. So let us call this vertex, I don't know, let's call this vertex V2. Okay? So V0 belongs to S. Now let S be V0 and another vertex V2. Everybody with me? Are there any questions at this point? Okay, good. If no questions, let us label the edges we have. V0, V1 is E0. H V1 is F. And then there is this edge at HV0. Okay. All right. Now what I want to do is, I want to go back to this edge E0, our original edge E0. Okay? I have some more information about the structure of the graph. So I want to go back to this edge E0 and draw some more conclusions about the neighborhood of E0 or the vicinity of E0. Okay? When I say vicinity, I mean the vertices and edges close to the edge E0. It's a vague term, nothing precise. Okay, so E0 we know that when we contract the edge E0, we know that we get a 3 connected graph, right? Because we applied Thomason's theorem to find the edge E0. So let's think about this. If you contract this edge and you get a 3 connected graph, then I think it means something about this component. I want you all to imagine, and I will make a drawing to help you, what happens when you contract the edge E0. When you contract E0 into a single vertex, let me call that vertex for the time being V0, V1, because it's the ends of E0. You get the vertex V2 here. Let me draw the graph like this. H is still here. H has 2 edges going to V0, V1, right? It's not a strictly contractible edge, so you expect multiple edges. This is the edge F. And what about the stuff here? If there is stuff here, what is this going to be? If this component is K, this will be the vertices of K minus V1.
I guess K contains only V1.
Exactly. If there are any other vertices in this set K apart from V1, if this is non-empty apart from V1, then what will happen is the only edges that K minus V1 will connect to is the contraction vertex and the vertex V2. In the graph G contract E0. And that means that this will be a 2 vertex cut in the graph G contract E0. That is a contradiction because this graph is 3 connected. Okay, note that if S, the cardinality of, okay, let me put some notation. Let K denote the component of G minus F minus S that contains V1. Note that if the cardinality of K, if it has at least 2 vertices, then V0, V1 and V2 is a 2 vertex cut in G contract E0, where V0, V1 is the contraction vertex. Okay? And this is a contradiction since G contract E0 is a 3 connected graph. Okay? So what we conclude is that the number of vertices in the component K has to be exactly 1, which means the only vertex in the component K is the vertex V1. Is everybody with me until this point?
So sir, basically we can say that V2 will be adjacent to V0, V1 in G contract E0, right?
Right. So yeah, we will draw more inferences, but is this part clear so far? Okay, so you're right. So now let's make some more inferences. Yeah.
Sir, because since V0, V2 is a 2 vertex cut, so we can say that every 2 vertex cut must have a neighbor in each of the components.
That's right. Yeah.
So in particular, V2 have a neighbor in the component K, but the component K contain only the vertex V1.
Exactly.
So hence V0, V2 will be adjacent to V1.
Right. So let's draw this graph again. This is S, this is V0, this is V2. There is a component here which contains the vertex H, but this component K is just one vertex V1. And V1's neighbors, now you can say it has at least 3 neighbors. So its only neighbors have to be V0, V2 and H. Okay? V0, V1 is the edge E0, V1H is the edge F, Okay, so we have found a vertex of degree 3. Does everybody agree? A particular vertex V1 has degree 3. From now on, when I have a degree 3 vertex, I will color it black. Okay, just to indicate that we know the degree. Okay, so let's make a drawing again. What do we have? We have the edge A, we have the vertex H, we have V0, V1, this is the edge E0. Yeah, I called it E1, E0, right? Yeah, okay, fine. I'll stick with that now. Okay, so we have these two edges, and V1 is a vertex of degree 3, which means it has exactly one more neighbor, and that neighbor we already know, we called it V2. Okay? Are there any questions or concerns at this point? All right. If not, now I want to look at this edge V1, V2. Okay? Let's call it E1. And this edge HV1, just to remind you, this is the edge F. Okay? So consider the edge E1, which has ends V1 and V2. Okay? Okay. Let us think about this edge a bit. We're going to argue that this edge is also contractible. So my claim is that E1 is a contractible edge. Okay? Well, so if it is not a contractible edge, then you might remember the lemma we used to prove Thomason's theorem. If it is not contractible, then its two vertices belong to a 3-vertex cut. Okay? If not, so let's prove this claim. If not, the ends of V1, V2, E1, sorry,
Where
E1 and
was
yeah,
that lemma 9.11?
yeah, 9.11. Yes, this is lemma 9.11.
Basically, there will exist a vertex W which will participate in a 3-vertex cut with the endpoints
Yeah,
of the edge.
yeah, exactly. Okay. All right. So these two vertices participate in a 3-vertex cut with some other vertex. Okay. Let's call this cut T. So this is a set T. This is V1. This is V2, and this is some vertex. Okay. And this is our edge E1. Okay. And when you delete these vertices, you will get some components. It could be many components. I am drawing 2 components right now. Okay. Good. But we have some information about the structure of this graph. V1 has exactly 3 neighbors, V2, H, and V0. Okay? V2 is here, but we know that V1 has to have at least one neighbor in every component, right? That is by one of your do-it-yourself exercises that we have used multiple times. So H has to be here and V0 has to be here without loss of generality. And these are the only 2 components. Okay? If there is any other component, then you will get a 2 vertex cut in the graph. Okay? Since degree of V1 is equal to 3, we conclude that G minus T has precisely 2 components. Okay? One containing H and another containing V0. Okay? But H and V0, they are joined by an edge. How is that possible? H and V0, they are joined by an edge. This is absurd, right? How can you have an edge between the 2 components? That is not possible by definition of a component.
Yeah, then G minus T will have exactly one component.
Exactly. So, so HV0 is an edge of the graph. Not possible. This is a contradiction. And that completes the proof, right, of the claim. So we assume that it is not a contractible edge and we arrived at a contradiction. Okay. So we have finished proving this claim. So what has happened? Let's take a quick look at what happened. We started with one E0, which is a contractible edge, but it is not strictly contractible by our assumption. And now we have another contractible edge next to E0. Okay? And now we can apply the same arguments as we applied to E0 to the edge E1. The vertices V1 and V2 must have a common neighbor. With E1 playing the role of E0, so one way to write this is with E1 playing the role of E0, we conclude that the ends of E1, V1 and V2 have a common neighbor. Okay, how can V1 and V2 have a common neighbor?
Sir,
So
this because E1 is not strictly contractible, right? That's why.
That's right. Yeah, it is not strictly contractible because we don't have any strictly contractible edges in the graph, right? So if V1 and V2 have a common neighbor, the only way that is possible is either V2 and H are adjacent or V2 and V0 are adjacent. Okay, those are the 2 possibilities. This implies that either V2 and H is an edge of the graph or V0 H, V2 V0 is an edge of the graph. At least one of these is true, right? I don't mean exclusive or. Is everybody with me? The only way for V1 and V2 to have a common neighbor is either V2 goes to H or V2 goes to V0 by an edge. Okay? So let's first look at this case. What if V2 and H are adjacent? You see, this is starting to look like a wheel, but it's not a wheel. It would become a wheel in this case if we put one edge between V0 and V2, but we don't have that edge right now. So this is not a wheel, but it's kind of like a wheel. Okay? So we are going to call this structure a partial wheel. And I will write down the definition of a partial wheel for you. Okay? But this structure that you see here, we are going to call it a partial wheel.
Basically, it's a wheel minus a rim edge.
Not exactly. I'm going to write down the exact definition of a partial wheel. Okay? But it's similar to what you said. Okay, so let's write down the definition of a partial wheel, and that is our special substructure. Okay, so let me put down the definition somewhere here on the side. In fact, we will call it a partial K wheel depending on the length of the wheel
Sir.
or the size of the wheel. Yeah.
So when you
Yeah.
write special substructure, you mean that it has that the graph G has that substructure as an induced subgraph, right?
No, as a subgraph.
Or only as subgraph, okay.
Only
So,
as a subgraph. If
so
there are
that
any other things that are inferred, that is a different story. But I just mean it as a subgraph.
subgraph, okay. So if the graph G has such a subgraph as a partial wheel, then V0, V2 may or may not be an edge.
Right.
Okay.
So what is a partial K wheel? It looks
About the
like
other
this. Sorry.
We are not inferring about the other edges in the substructure. Only those edges
Right.
are.
Right. Exactly. So what we want is a path V0, V1 up to Vk, and the edges of this path we will call them E0, E1 up to Ek minus 1. Okay? And we have this common vertex. We have this vertex H, which is called the hub of the partial K wheel. Okay? Which is not on this path. Okay? I'm not writing down the whole definition. Okay? So we have the path, and we have this hub, and we have the following properties. So path is V0, V1 up to Vk, and hub H, which is not a vertex of the path. This is the path P. Okay? And we want the following properties. We want the hub to be adjacent to every vertex on the path. We want all the internal vertices of the path to be cubic. So we want Vi to be a cubic vertex, degree 3 vertex for all I in 1 up to K minus 1. Okay? So all of these have to be cubic vertices. Okay? So there you kind of see that is an induced subgraph there, but the whole subgraph may not be induced. Yeah.
But say 2 follows from 1, right? The condition 2 follows.
Why does it follow from 1?
Because since we have a path, every internal vertex of a path has degree 2, and we know that H is adjacent to every vertex of the path. That means
Yeah,
that
but why can't it have degree 100?
no, it can have degree 100. Then
Right.
it can
So
be
this
adjacent
is
to some other vertex.
cubic in the graph G.
Okay.
Okay. So not
So
cubic
basically
in this
you are saying
structure,
that path
but it
is
is
induced path.
Yeah. This path is like this. There is this part of the partial wheel which is like an induced subgraph, but the
Yeah.
whole subgraph is
So
not
this
necessarily
path is
induced.
induced path in this subgraph.
Right. Exactly. And the last edge we want it to be contractible. Okay. The last edge, which will be Ek minus 1, is contractible. Okay. So notice that this definition, if you think about this definition in our structure here, It satisfies, right? This is a partial
But
two
sir,
wheel.
I have a question.
Yeah.
So the notion of a contractible edge we define for three connected graphs, but a
Hmm.
partial K wheel is not three connected because the
Yeah, it
degree.
is not. It is not. It is a subgraph of your three connected graphs that we care about.
Okay, but sir, when you are saying that it has a contractible edge, Vk minus one Vk.
In the original graph G. So this definition, it is a partial K wheel
Okay,
um,
sir.
in the graph G. So most things here are with respect to the graph G. So it is contractible in G. Okay. Yeah. So I agree that it can be confusing if you are not distinguishing between the structure and the original graph. So it is contractible in G itself. Okay. So this is for a three connected graph G, where G is simple and three connected. Okay. So now, do you all agree that this is a partial two wheel?
So can you show partial K wheel again?
Yeah, sure. Yeah, sorry that things are a bit far away from each other. So you have this path, you have the hub, which is adjacent to everybody in the path. All the internal vertices of the path have to be cubic. And the last edge of the path has to be a contractible edge in the original graph G. That is all the properties we are going to require.
Okay, okay.
Okay?
Yeah.
Good. All right. So we have a partial two wheel. Everybody agrees this is a partial two wheel. Okay, good. Now let's go to the second case. The second case was when, so if this is an edge of the graph, then we have a partial two wheel in the graph G. Okay. Now I want to look at this case. I'm going to draw it here again. So we have the vertex H here. We have the edge V0, V1, which we started with. This is our edge E0. These two are neighbors, right, of H. And then we found another edge. This is the vertex of degree 3. And we found another edge E2. Okay? And this is the vertex V2. Sorry, not E2, E1. E1, and this is V2. And now we are considering the possibility that V0 and V2 are adjacent. Okay? I claim that this is also a partial two wheel. You just have to redraw the graph. So let me redraw the graph for you. Put V0 here and notice that H, V1, V2, they form a path. H, V1, V2. Okay? E1 is still this edge. And V0 is adjacent to H, V1 and V2. V1 is still the internal vertex and it has degree 3. And E1 is still a contractible edge as we want it to be. So this is also a partial two wheel. Okay? Does everybody agree? This is a partial two wheel.
Basically, it's just a matter of drawing.
Exactly. It's just a matter of drawing. Fine? All right. So what we have shown so far in this proof is that the graph has a partial two wheel. Okay? That completes the step 1. Now, to be honest, I was thinking that I will get to almost step 2 by this point, and then we will have just step 3 to complete, but that is not where we are. So I don't mind stopping the proof here and completing on Monday and starting module 3 from Wednesday. Also because I think you might be tired and some of you might have to go to other classes and all. So I don't mind stopping here and continuing the proof on Monday, unless there is
Sir,
a, yeah.
I think it is the longest proof which I have encountered in the graph theory.
Okay, yeah. So I think now I'm rethinking my position. Last night I was excited. I was like, oh, I want to show you the whole proof in one lecture. It will be so good. But now I'm reconsidering my position, and I feel that it might be better to stop here and give you all time to digest what we have seen so far, and continue from here on Monday and start the next module from Wednesday. Unless there is a strong, good number of people who want to see the whole proof today, in which case we might need another 30 minutes. Okay, so if you really want to see the proof today, then turn on your mic. Otherwise, we conclude the lecture here. So even the last semester, I think I took 2 complete lectures to prove this. So I don't know why I imagined it would be any different this time.
Sir, can you complete the proof?
One person saying that. Let's see how many people we have in the meeting. Sorry?
It's okay for me if you complete the proof today.
I see. Let's see how many of you. So how many people are there in the meeting? 1, 2, 3, 4, 5, 6, 7. So 2 people are willing to see the whole proof today. What about the others? If we get at least 4 people who are willing, Girija auditing. Yeah, I would rather wait for 2 more auditing students. I believe Yuvraj probably has a quiz at 10 o'clock. Do you?
I don't have a quiz, but I have a class.
Right, you have a class at 10 o'clock.
Yeah.
So, yeah, to be honest, after seeing how many people are there in the meeting, I am not too keen on completing the proof today. There's very few people in the meeting. Are there any others who really want to see the proof today? Okay. So we have only 2 people who are willing to see the proof today. So let's not go there. Let us, and I think even for you, it might be better to actually go through what we have done so far, and then to look at the steps 2 and 3. So I will tell you what the upshot is. If you are interested in trying to prove on your own, I can give you the upshot of the proof. We have shown the existence of a partial K-wheel. Okay? So the rest of the proof, what it does is, it takes a partial K-wheel with a maximum value of K, right? And then you have to argue that the graph has to be exactly the wheel. Okay, so that step 2 is to take a partial K-wheel with K maximum. Okay, and then using similar arguments as in step 1 to conclude that the whole graph is just a wheel. Okay, that's how the rest of the proof goes. So if you're interested, you can try doing it yourself. And many of the arguments are similar to arguments you have already done. So there is going to be quite some repetition, which can be reduced, but that is a matter of writing. And my intention here is to explain things rather than getting a shortest proof, right? So there will be some repetition, but that can be avoided if one is careful. Okay, so let's stop here. I think it's better to continue on Monday. I'll stop recording now.